Welcome to Inequalities and Systems for Pre-Calculus of Math 11. Today we're going to take a look at graphing linear inequalities. Basically, when we graph a linear inequality in two variables, how we graph the line changes based on if the question has an equality or not. And I don't mean how we graph the line in terms of rise over run, y-intercept idea. I'm talking about physically, do we draw a solid line or a dotted line? So the less than and greater than signs are represented by a dotted line. So if we see that kind of sign, we're going to represent the line with a dotted line rather than a solid line. And the less than or equal to and greater than or equal to signs are represented by a solid line. So not terribly difficult in terms of how we do it. It's the exact same as graphing just a regular line, which we've done a lot of, but more about should we make it a dotted line or a solid line. So steps for graphing linear inequalities, very basics. We're going to graph the line using the standard form of the equation, and standard form for a line is slope y-intercept, or that y equals mx plus b. Now make sure that you don't forget to make the line either dotted or solid based on the inequality sign. And what we're going to do is maybe just graph it regularly, and you can erase it if you want to make it dotted, or just draw it dotted from the get-go. So what we want to do then is we want to shade the desired region by selecting it in one of two ways. So because we're talking about an inequality, we're talking about shading, and what we want to do is we want to shade in the region which matches the inequality. One way to do this is to choose a test point which is not on the line. I can't stress that enough. It can't be on the line. May I suggest that 0, 0 can be easy. A lot of times 0, 0 is nowhere near the line. You might as well use that. It's an easy point to test. If it's kind of close, you know what? Don't take chances. Choose the point 10, 10, 100, 100, or even below negative 10, negative 10, something like that. So plug that point into the linear inequality. If it satisfies that inequality statement, so if it's true, if it works, then shade that side of the line that you picked. If it does not satisfy the equality, i.e. if it's false, then shade the other side of the line. That's one technique to look at. The other technique is if the y value is less than the equation, then you want to shade below the line. If the y value is greater than the equation, you want to shade above the line. This technique works. It's a little bit easier, a little bit more conceptual, but it's also based on doing one or two intermediary steps, which might mess this up a bit. So what do I want to do? Let's start with our equation. 3x plus 2y is greater than 6. Let's put this into slope y-intercept form. Now remember, the only real big stipulations we have is when we're solving linear inequalities, or inequalities in general, when you multiply or divide by a negative number, we need to flip the sign. So here we just subtracted 3x to the other side. That's not a big deal. And here we divide by 2. So we get negative 3 halves x, and 6 divided by 2 is 3. So there's our slope y-intercept form. Let's take a look at this. So we have plus 3, 1, 2, 3. Let's draw a dot on that y-intercept of 3. Let's take a look at a rise over run of negative 3 halves. So it rises 3 and runs 2, and this is sloping up and left, or down and right, depending on how you want to look at it. So I'm going to put multiple dots along there. And here's the idea of the dotted or solid line. It has to pass through all those dots. If it was an inequality with an equal sign, we would draw a solid line, but in this case I can just draw a dotted line in because it doesn't have that equal sign. Let's put some arrows on the end there. Let me try and get my whole graph in here. There's a point, and put some arrows in there. So there's the equation itself, there's the line itself. Now we want to figure out which region satisfies this. The second method, that 2b method where you just kind of look at it, has to do with these values. So once I get down to here, here's my y values. That y represents all the y values, and all those y values have to be relative to this line bigger. So I want all the y values that are bigger than the line, that are above the line. Now, you know what, that doesn't work too bad when we talk about solving. The only problem is we're almost using secondary information here. Let me shade that in. We're using secondary information, and what I mean by that is that we are taking an equation, the original 3x plus 2y greater than 6, and we're doing a little bit of math, a few math steps to turn it into standard form. Typically, you always want to base your information on the original question. So that's one way to do it, but we could also test a point. 0, 0 is clearly not in our on our line. So let's test the point 0, 0. So let's go back actually to the original equation. That's usually your best bet. We want to see if 3 times 0 plus 2 times 0 is greater than 6. That's 0 plus 0. Is that greater than 6? Is 0 greater than 6? And that's one of those heck no's. So what we do is we shade the other side of the line. So we tested 0, 0, it didn't work out, so we have to shade the other side of the line, which I've done already. I shaded the side that's above the line. We could work a little bit backwards here. We could start with a shaded region and try and figure out the equation. I'm going to graph, let's say, or pick this line off on the left here, and we'll let you do the one on the right. So I see a y-intercept of -2. We're rising 1 for a run of 3. So it's a rise of 1 for a run of 3. So we have 1/3 minus 2. It's a y value. So it's y equals 1/3 x minus 2. Now, it's a solid line. I know it might look a little bit dotted, but it's supposed to be a solid line. So it's going to have an equality sign. And do I want all the y values that are bigger than that line or smaller than that line? I want all the y values that are above that line. So y is greater than or equal to 1/3 x minus 2. Why don't you hit pause here, see if you can figure out that B answer. So we have a y-intercept of 1. We have a rise of 2 for a run of 1. So it's 2 over 1. Let me just write it like that maybe for now. And the y-intercept was 1. It's a dotted line, so it's going to be an inequality. And it's negative because it's rising 2 and running 1. And we want all the y values that are below that curve. So y is less than -2 x plus 1. Word problems we get into a little bit more of a challenging idea, I think. Just remember that every word in a word problem represents some mathematical symbol. So little Lenny Leonardson has $12 to buy seeds for his mommy's garden. A package of vegetable seeds costs $2, and a package of flower seeds costs $1.50. So there's always going to be some total thing, in this case total money of 12. And then there's going to be two different variables going on here. Vegetable seeds cost $2 and flower seeds cost $1.50. So let's use maybe just a let statement to keep things a little bit clear for us. Let's use y equals the number of veggie seeds bought, and let's use x to represent the number of flower seeds bought. Now you can use whatever variables you want. I find that x and y kind of translate nicer to graphs. It doesn't really matter. You can label your graph however you want. So let's figure this out. Write an inequality represent the total cost of the seeds. Well, little Lenny Leonardson here has $12. That's as good as it gets. That's got to be the bigger of the two. And it can also equal. He could go to the store and spend exactly $12, or he could spend less than that. So $12 is the upper limit. If we take the number of vegetable seeds he bought and multiply it by $2, that works out. And if we add to that $1.50 for every flower seed he bought. So let's change this right away into fractions. $1.50 or 1.5 is the same as 3 halves. Let's turn this into slope y intercept form by subtracting negative 3 halves. X plus 12 is greater than or equal to 2y, and then dividing by 2. We end up with negative 3/4 x plus 6 is greater than or equal to y. So we have an equation that represents this buying idea. This is the x-axis, which represents flower seeds. The vertical is the y-axis, which represents veggie seeds. Number of veggie seeds bought. Let's graph this equality. It's shifted up 6. 1, 2, 3, 4, 5, 6. Has a slope of negative 3/4, so let me drop 3, run 4. Drop 3, run 4. Let me graph this in there. This is an equality, so it could equal that value. So we're going to have a solid line. I know mine looks a bit of a kink in there. It's not supposed to really be in there. If we think about this, there are some little restrictions that do occur. X and Y must both be positive. It doesn't make sense to say that he can buy a negative amount of seeds. So when we shade this in, we want the Y values that are below the line. So let me shade in below the line, and notice I'm only going to shade in above the axis, above the x-axis that is, and below, or sorry, to the right of the y-axis, because that region defines all the positive values that work for this kind of seeds situation. So when we get into, can Lenny buy 4 packages of vegetable seeds and 2 packages of flower seeds? Let's check how much change he'll have left over. What we can do is we can just plot a point. Can he buy 4 vegetables? So vegetable is vertical. 1, 2, 3, 4. And 2 flower seeds. It looks pretty close. Let's test it out. I think yes. I mean, it could be I didn't graph it very well, but let's take a look. We want can seeds are X and flowers are Y. So let's check this out. We have, let's go back to our original equation. Don't want to mess this up by doing some intermediary steps. Is 12 bigger than or equal to, larger than or equal to 2 times 4 plus 1.5 times 2? That's 8. 2 times 1.5 is 3. And 8 plus 3 is 11. You betcha. So yes, he can. How much money does he have left over? Well, because the difference between the two sides are 11 and 12, little Lenny Leonardson has $1. A funky one there. $1 left over. So really the difference between the two sides. This ends the notes for graphing linear inequalities, section 5.2.